Morning, I will talk about molecular contrast agents for visualizing certain aspects of plaque particle biology. So Mike has given an introduction into the different processes that play a role during plaque formation and progression or regression. And what I want to do now is take the standpoint of the contrast agent, so to say, in the imaging modality that we're going to use, and see what sort of concepts are most fruitful for visualizing certain of these processes that are key to atherosclerosis. So I will talk about the choice of contrast agent, and of course then we also need to think about the imaging modality that we're going to use. I'll give you a couple of examples as to the sort of approaches that are people taking nowadays and what the information is that we can gain from this molecular imaging of atherosclerosis. And I will end with showing an example of how this technology can be used to guide therapy and intervention. And I will end with a few concluding remarks. So first of all, of course, the design of a contrast material depends a lot on the imaging target that we want to visualize. The type, is it a protein or an enzyme or a cell type perhaps? Where is it localized and how abundant is it? And of course, that needs to be combined with the characteristics of the imaging modality of choice. Let me give you a few examples as to the sort of things we need to consider. Suppose we are to image vascular endothelium, receptors on vascular endothelium that we know are present early on in atherosclerosis development, but then occur in low concentrations. And of course they are expressed only in a very thin layer of endothelial cells. So we need to design then contrast agents that are capable of generating sufficient signal to capture these guys. So that has led to a situation that in many cases people take targeted nanoparticles in this particular setting. We can put in a lot of contrast agent, and they are initially mainly restricted to the vascular compartment so that we have a reasonably high target to background ratio, not too much leakage into the plaque itself. And this approach is being used by all major imaging modalities, and quite often in a multimodal fashion even. Another example, structural components of the extracellular matrix, like elastin or collagen. In this case, we often have abundant target, quite often densely packed. And in that particular case, then a low molecular weight agent would be favorable because it would have good access to the intended target. But again, it could well be that we would like to rather look at more disorganized state of the extracellular matrix during remodeling, for example. And then again, a nanoparticle approach could be quite attractive to more or less specifically visualize this disorganized extracellular matrix. As a final example of considerations, suppose we want to probe metabolic status of the plaque. For example, inflammation is associated with elevated glucose use. Then, of course, in order to probe that with our imaging technology, we need an agent that is closely related to, for example, in this particular case, the glucose molecule. And because it needs to be taken up into the cell through the glucose transporter, be converted by the enzyme hexokinase, and then be trapped in the intercellular compartment. Only if you have an agent that is so closely related to glucose that these processes still are possible, and can we really get a good sign of the, in this particular case, metabolic glucose use. So, and let's now talk about the contrast materials itself. So, of course, we need some sort of recognition. And depending on the sort of material that we want to target, we quite often make use of antibodies, peptides, aptamers, etc., etc. And these, of course, need to be linked to agents that are going to generate an imaging signal. And then it depends, of course, a lot on the imaging modality that we're going to use. I will not spend too much words on that, and the sort of options that we have. There's either a capability of direct detection or indirect detection that we mostly do in case of MRI. So then in the end, we will have a structure like, for example, in this particular case, a nanoparticle that is equipped with a monoclonal antibody for target recognition. And this has led, all these developments have led to a plethora really of imaging agents that have been developed for target-specific imaging, including for atherosclerosis, ranging from small ligands with low molecular weight, easily accessible into the plaque entirely, all the way up to nanoparticles. And in between we have active site binders, sensing agents that are being activated by enzymes, etc., etc. And of course we also need to consider the characteristics of the imaging modality that we're going to use. And we are working in this triangle of sensitivity, spatial resolution, and scan time, but also would like to consider perhaps how versatile is our technology. Can it not only provide molecular imaging information, but for example also report on functional status of the tissue or its microstructure, etc., etc. Translatability could be an important issue. Can we both apply it in the animal model setting and in man? And of course, boring practicalities like costs and availability. So let's look now at a few examples of the technology that has been developed for molecular imaging of atherosclerosis. And I've decided to focus on the topics indicated in bold to the left. So endothelial cell activation, being there all the time, but especially in the early phase, macrophage activity, oxidative stress, proteases, extracellular matrix and thrombus as a sort of final stage. And I'll also briefly touch upon therapeutic interventions and what our technology can offer there. So first on this endothelial cell activation, well, we basically aim to visualize markers, adhesion molecules that are expressed on the vascular endothelium. And as I indicated earlier, it's quite attractive to use a nanoparticle approach in this setting. And this has been explored, for example, by the Oxford group with the use of micron-sized particles of iron oxide. They generate a very strong MRI contrast change on T2 star weighted scans, and also they are restricted to the vascular compartment, largely. And the other nice thing about them is that we can directly visualize them with light microscopy, as is shown here on this microscopy slide. So this is a very effective agent, and it's been explored by the Oxford group to target adhesion molecules. So here we look at the level of the aortic arch, where you can see these signal voids be generated by these large particles of iron oxide, in case of a functional agent, but not in case of a non-functional agent. And it turned out that when these authors examined a dual targeting at the same time on the same particle, P-selectin and VCAM1, that's this bar, that this led to the most effective labeling of the vascular endothelium. So a very powerful approach. So this is MRI. In this setting, ultrasound is also a very attractive technique to consider. Also here, micron-sized particles are being used. An example of that is shown here, because they have sufficient detection sensitivity to be visualized on ultrasound scans on the basis of the cavitation properties of these materials, as is shown here. So these can be made targeted as well. And then we would have a targeted agent that would target to vascular endothelium. But you realize that because these particles are so big, that we not only need to consider the properties of the agent or the properties of the target that we want to visualize, but also now hemodynamic properties come into play, because shear forces exert action on these nanoparticles and have a very big effect on the sort of targetability of them to the vascular endothelium. But then, this is a very successful imaging modality for this type of work. As shown here, plaque progression, increasing oilite O staining, increased VCAM1 expression, and then also the contrast-enhanced ultrasound scan using VCAM1 targeted material. As you can see, it generates stronger signal chains in the more advanced plaque. So it's very powerful technology also for looking at vasovasorum, for example. Now back to MRI and looking at macrophage activity as a next stage of the process I would like to show to you. Traditionally, MRI is a very powerful technology here because iron oxide nanoparticles that we can visualize on T2 star weighted scans are internalized by macrophages quite effectively. And this property has been exploited in the study I'm showing here to look at a treatment effect. In the treatment group, the plaque is smaller, also seen on histology, and leading to lower macrophage count, as you can see here, and also reduces the T2 star change that is induced by the injection of the iron oxide nanoparticle. So we have a setting where an in vivo MRI readout can report on the efficacy of a therapeutic intervention. We have, along similar lines, done a lot of studies using lipid-based nanoparticles, again for MRI, but now labeled with a gadolinium chelate for T1 contrast. And what we typically have is a contrast agent like this, so it's a lipid molecule which is embedded in these particles that I show in the upper part of the slide. And coupled to that, we have this gadolinium DOTA moiety for MRI contrast. And we've used these, for example, to look at macrophage targeting in advanced plaques, work pioneered by Willem Mulder in our group. And so we have CD204 mice cells, which are targeted to a scavenger receptor expressed by macrophages in the plaque. And as you can see, in these mice cells, they generate a very strong signal change in the abdominal aorta, which we can nicely analyze. So these are nanoparticles for macrophage activity. Now to a low molecular weight agent that is used to probe an aspect of inflammation, and that is myeloperoxidase activity, which is expressed abundantly in atherosclerotic plaques. So the concept that's being explored here is that to use a low molecular weight agent, the one indicated here schematically, that by the enzymatic activity is radicalized and then oligomerizes. And this has two major consequences. First of all, the detection sensitivity is improved because we get a higher ionic relaxivity, but also the retention is prolonged. And this has been explored, for example, the utility of an agent like this in a rabbit model of atherosclerosis by the Stanford group. Here, first of all, you see that in a diseased wall, in this rabbit model, the MPO activity is a lot higher than in a normal wall. And then the agent was tested. Please look at this part of the slide where we see at 2 hours after injection the MPO-specific gadolinium agent, giving rise to a very strong signal change in the abdominal aorta, whereas gadolinium DDPA, the non-specific agent, non-targeted, right, extracellular agent, does not give rise to any signal change any longer. So this is a very effective way of visualizing expression of the MPO enzyme. And indeed, when comparisons were made between the MRI-positive area detected in vivo to the ex vivo immunohistochemistry of the MPO-positive area, there's a very nice correlation there. So that's enzymatic activity probed with a low molecular weight MRI agent. Then nuclear imaging techniques, because of their superb sensitivity, have a very important role to play. And I'll show you two examples now. First of all, of an sort of inflammation activity scan with PET-FDG, very high resolution in a cast model, a carotid cast model in EPO knockout mouse, where here this is a hotspot visualized with the FDG scan, very close to the cast, which leads to the formation of an atherosclerotic plaque. So there's very high spatial resolution microspect studies done in Münster, Germany. The same group also develops low molecular weight MMP specific agents. These are 18-fluorine labeled agents. And in the same animal model, you can see here a hotspot of an MMP inhibitor at a location where later MMP tomography indeed showed the enzyme to be present. So nuclear imaging is important. For small animals and invasive procedures, optical techniques also can contribute a lot to atherosclerosis imaging and biological understanding. I'm showing one example of that. Studies pioneered by Matthias Narendorf from Boston, who's developed a fluorescence molecular tomography technique, where the 3D spatial distribution of an optical agent can be very nicely visualized at the whole animal level. I'm going to show one example of protease activity detection, where a nanoparticle is being used that in its native state has quenched fluorescence, so it's silent in the assay, so to say, and now by cathepsin activity, so that's a protease, the quenching is relieved and the agent is visible on the FMT scan. And he has used this, for example, to probe statin activity, lowering the protease activity. Here a scan where the a native animal is tested, and here an animal on aggressive statin therapy. You can see there's a tremendous reduction in the signal intensity. So that's protease activity. Now to extracellular matrix, where MRI is the main technology, I would say, because of its high spatial resolution and superb soft tissue contrast, where we can very nicely visualize even tiny vessel walls in small animals, like we, for example, do in Eindhoven, but even better by the group of René in London, where they've shown beautiful examples of the use of an elastin-specific MRI contrast agent. So it's a low molecular weight agent, shown here. This is the MRI reporter group, and this is basically the moiety that interacts with elastin with appreciable selectivity and affinity. And they've shown, for example, in this study, that with plaque progression, where there's more elastin deposition in the plaque, that also the signal change that is induced by the injection of this contrast agent is increasing. So, for example, in this graph, you can see that any positive agent, functional agent, over time on a high-fat diet shows in the APU knockout mouse increased signal change, whereas the non-functional control, the gadolinium DDPA, does not show this effect at all. And this assay is also sensitive for statin therapy, as you can see here. So recently the group took this to a large animal model, a pig. I'm not sure whether it was on a high-fat diet, but it had appreciable plaques. And what is shown here at the level of the abdominal aorta is a comparison of gadolinium DDPA, so the non-targeted agent, clinically approved, to the elastin-specific molecular agent that I just described, showing very nicely highlighting the vessel wall in this pig model. So this can be used along with the MRI technology that René just showed to very specifically highlight the vascular vessel wall where there's appreciable elastin expression going on. So now back to a mouse, still extracellular matrix visualization, but now targeting collagen. We've done quite a few studies to target collagen in very tiny plaques, early stage plaques, where there's not a lot of collagen present yet. And we do this in an animal model, APOE knockout mouse, where we place around the right common carotid artery a polymeric cast, which leads to the formation of tiny plaques on either side, slightly differing in collagen content. And then we probe for collagen distribution using this micellar contrast agent, so it's a nanoparticle around 25 nanometers in size, that we equip with a collagen-seeking protein, CNA35, using a mutant protein as a non-functional control. And then this is the data. So this is slices through the neck of the animal. This is the non-lesioned vessel, and this is the lesioned vessel. This is the upstream and the downstream location using a functional agent. We do see a nice signal change in the lesioned wall, but not in the other one, and a non-functional agent basically shows very little effect. Now this self-same concept of the collagen-seeking agent has been explored in New York by Willem Mulder and Sai Fiat and colleagues at Mount Sinai in a very nice animal model of abdominal aorta aneurysms. And they find very strong signal enhancements in case of a lot of collagen deposition in the AA lesion, and a lot less signal change in case there is a lot less collagen. So very effectively showing collagen distribution in this particular vascular lesion too. So then, as a sort of a final stage of atherosclerosis development, plaque rupture associated with embolus formation, thrombus formation, and fibrin in there, there's a lot of studies going on to target fibrin as a very attractive tool for molecular imaging of atherosclerosis. We do work on that using SPECT imaging. So this is a probe which was recently synthesized by Luc Starmans, a functional fibrin binding peptide, and this is a non-functional control that he equipped with a spec ligand in this chelate moiety, a spec label, so a gamma emitter. And then this shows in two different orientations that there's a very strong signal change in case of the functional peptide for a thrombus model in the mouse carotid artery. And you can see that the non-functional peptide does not show any signal change. And indeed, quantitative evaluation shows that there's a very strong effect of uptake into the thrombus in case of the functional peptide and not with the non-functional peptide, and only in the injured artery and not in the non-injured carotid. Actually, this type of approach, low molecular weight agent, but now labeled for MRI detection, has been explored in first-in-man studies by Elmar Spuntrup and René Bodnar and colleagues. And very, very nice studies. He is showing on the T1 weighted scan a very nice delineation of an embolus, also seen on CT, with very good sensitivity and contrast to noise ratio. So I've given you a couple of examples of molecular agents for detecting certain aspects of plaque pathobiology. Of course, what we've been using for targeted imaging is also often used for targeted therapeutic interventions. So the technology that has been developed is also very well suitable for monitoring the consequences of therapeutic interventions. I'm going to show you one example of that in recent studies in a rabbit model in New York, where a nanoparticle formulation of an anti-inflammatory agent was used, a glucocorticosteroid that is encapsulated in the lumen of this liposomal nanoparticle that was also equipped with an MRI label and a fluorescent label in order to detect its delivery to the plaque following injection into the rabbit. So an MRI readout was used for agent delivery monitoring, and FDG PET was used to monitor the anti-inflammatory effect of the agent. So this is a readout of delivery of the agent using T1 weighted MRI. You can see a signal increase after liposome injection. So the material is going, the paramagnetic liposomes are going to the plaque, and they have a beneficial effect because they lower on the FDG PET scan the specific uptake value only for the nanoparticle associated drug, not for the free drug, as you can see. And so this shows that by combining different imaging modalities and equipping the therapeutic agent with a diagnostic agent can really help understand the efficacy of, in this particular case, anti-inflammatory intervention. So I've shown you a couple of examples of the many examples that I could have taken of successful molecular imaging of atherosclerosis using many different approaches, basically targeting any molecular process that Mike has talked about in his first lecture, with basically all imaging modalities. And I think that and this technology will have both consequences at the level of the diagnosis of atherosclerosis, but also can aid in developing more improved therapeutic interventions. And I think we'll also see further examples of theranostic approaches where the two are combined. With that, I want to stop. I want to thank these international and national collaborators for collaborating with us in this field of molecular imaging, not just for atherosclerosis. And I'm very grateful to our team in Eindhoven, not all of them working in molecular imaging, but quite a few do, because they create this stimulating atmosphere to do this type of science. You know what I mean? And of course we need some money in order to do this work. And I want to thank you for your kind attention.